Hello everyone. So in this video lecture I am going to discuss the techniques that I use to design the first order parallel processed IIR filter. Hello everyone. So in this lecture I am going to discuss the techniques that I use for deriving the parallel processed IIR filter structure, and I am going to consider a first order IIR filter given by the transfer function hz, that is equal to z inverse divided by 1 minus az inverse, where the magnitude of A is less than equal to 1, that is for stability. So this filter is having one pole located at Z equal to minus A. So you can calculate this easily by equating the denominator to 0. So this filter can be represented by equation in time domain given by yn, that is equal to A of yn minus 1 plus x of n minus 1. And this can be represented by using a block diagram where xn is delayed by one cycle and y, that is multiplied by e, and then it is delayed by one cycle, and the two quantities are being added. Okay, so this delay element can be placed before multiplier also. Okay, so this can be easily done by the retiming technique. So the critical path, talking about its critical path, this will be the critical path, and the critical path time will be Tm plus Ta. So Tm is the computation time of multiplier and Ta is the computation time of adder. So Tm plus Ta. And talking about its sampling rate, so T sampling rate will be equal to critical path time. Okay, so for this given filter the maximum sampling rate will be Tm plus Ta. So if we want to increase this, then we have to either pipeline this system, or the alternative is parallel processing. We can increase the sampling rate by parallel processing. So pipelining of an given IIR filter has been already discussed in my previous video lectures, and there the look ahead transformation technique was used, and the same technique will be used for deriving the parallel blocks for the same filter. So suppose I want to increase the sampling rate by factor 2. Okay, so I have to design or derive two parallel architecture for this filter. Okay, so I'm going to take this filter as an example, and for this filter I'm going to design the two parallel architecture. So the filter under consideration is given by the equation yn is equal to A of yn minus 1 plus x of n minus 1, and for L equal to 2 we can update the equation in this form. So y of 2k, that can be written as a into y of 2n minus 2k minus 1, this should be k, plus x of 2k minus 1. Okay, so in place of n just put 2k, and the second equation, now in place of n put 2k plus 1. So y of 2k plus 1 is equal to a into y of 2k plus x of 2k, and the two parallel structure can be visualized something like this. So a bigger block which is having two smaller blocks inside. The first block is processing input x of 2k, and it is generating the output y of 2k, and the next block, it is processing the next sample, that is x of 2k plus 1, and producing the output y of 2k plus 1. So these two samples, x of 2k and x of 2k plus 1, are being processed at the same time, and corresponding output, that is y of 2k and y of 2k plus 1, are being generated at the same time. Okay, so after this completes the first iteration. So after this The second iteration, the upper block will process the sample x of 2k plus 2, the lower block will process the sample x of 2k plus 3, and the output will be produced y of 2k plus 2, that corresponds to the input x of 2k plus 2, and the output y of 2k plus 3, that corresponds to the input x of 2k plus 3. Okay, so for this the delay element will be referred as a block delay. So the block size L is 2 because it is processing 2 samples simultaneously. So block size is 2. So if the input is xk, so it would have been stored x of k minus 2 previously. Okay, so from this point you can clearly visualize this. If x of 2k plus 4 is the present sample, the previous sample would have been x of 2k plus 2. The difference is of 2. Okay, and previous to this the sample would have been x of 2k. Same case here, the difference is of 2. Okay, so for this reason the delay element is considered as block delays. So block size is 2, the difference will be of 2, it is xk, the output will be xk minus 2, means that it had stored the input that came 2 cycles before. Okay, so now because of this there will be a problem. So you can see in equation 1 that y of 2k is equal to a of y 2k minus 1. So yk is dependent on the input sample that came 1 cycle before, that is x of 2k minus 1, and the output sample that was generated 1 cycle before and multiplied by a, y of 2k minus 1. Okay, but if I derive the parallel FIR structure, the delay element will correspond to the block size. Okay, so if I put a delay element, then there will be a difference of 2. So it is not possible to feed back the term y of 2k minus 1. So because of this we have to modify this equation, and that we will do using look ahead transformation technique. Okay, so now in this y of 2k minus 1, considering this term y of 2k minus 1, so this would have been calculated using x of 2k minus 2 and y of 2k minus 2. So y of 2k minus 1, that is equal to a into y of 2k minus 2 plus x of 2k minus 2. This is equation 3, and substituting equation 3 in equation 1. Okay, so putting the value of y of 2k minus 1 in this equation, we have y of 2k, that is equal to a inside bracket a into y of 2k minus 2 plus x of 2k minus 2, this term, plus x of 2k minus 1, this term. Okay, opening the bracket and multiplying a, we have y of 2k is equal to a square y of 2k minus 2 plus e of x 2k minus 2 plus x of 2k minus 1. Okay, and in the same equation, instead of 2k I can put 2k plus 1. So y of 2k plus 1 will be equal to a square y of 2k minus 1 plus a into x of 2k minus 1 plus x of 2k. So now I have two updated equation 4 and 5. Okay, and here you can see that the difference between the output sample and the delayed output sample is of 2, y2k, y of 2k minus 2, y of 2k plus 1, y of 2k minus 1, the difference is 2. So now I can easily feed back the delayed sample. Okay, so now I have to implement equation 4 and 5. So the block diagram for this two equation will be something like this. Okay, so this is y of 2k, that is equal to a square y of 2k minus 2. So this multiplied by a square and delayed by one delay element. Okay, so the output will be a square into y of 2k minus 2 plus a times x of 2k minus 2. So x of 2k delayed by one cycle will give x of 2k minus 2, that multiplied by a. Okay, so x of 2k plus 1, when it is delayed by one cycle, the output of this delayed element will be x of 2k minus 1. So this is added to this term. So this represents the first equation. And the second equation, y of 2k minus 1. It is producing y of 2k minus 1, the lower one, that is sum of a square y of 2k minus 1. So y of 2k plus 1 multiplied by a square and delayed by one cycle. So the output will be y of 2k minus 1, difference will be 2, plus a into x of 2k minus 1. So this is x of 2k minus 1, that is multiplied by a, and this will be added to x of 2k. So this is added to x of 2k. So this is the two parallel IIR filter architecture of the considered filter. And the sampling rate. So now talking about its hardware complexity. So in the upper block you can see that total number of multipliers are 2, and in the lower block the total number of multipliers are also 2. The total multiplier is 2 plus 2, that is 4, and 4 is L square. Our value of L was 2, so 2 square is 4. So in general case, if we design L parallel filter, total number of multipliers required will be L square. So hardware complexity increases by L square. Okay. So in the sequential filter, the multiplier was 1, and in the two parallel IR filter the multipliers are 4. Okay, so hardware complexity increased by 2 square, that is 4. So for L parallel filters, total multipliers required will be L square. So hardware complexity will be increased by L square. So now to reduce the hardware complexity, that is reduction in the number of multipliers that are being used. Okay, and why we are focusing on especially on multipliers, because compared to adder, the multiplier takes large amount of area and the computation time is also comparatively more. Okay, so that's why we are more focused on the multiplier part. So suppose if we want to reduce the number of multipliers, so what we can do, we can use the incremental computation technique. And how we can use that? So y of 2k plus 1, the second term y of 2k plus 1, that can be computed from y of 2k. Okay, using the equation y of 2k plus 1, that is equal to a of y of 2k plus x of 2k. That was our original equation. So we have started with this equation. So what we are doing, instead of designing a separate block that will produce y of 2k plus 1, we will compute y of 2k plus 1 with the help of y of 2k. And for y of 2k we have already designed a block. Okay, so y of 2k will be given by the same equation. Y of 2k is equal to a square y of 2k minus 2 plus a into x of 2k minus 2 plus x of 2k minus 1. Same structure. Now y of 2k plus 1, it is a into y of 2k. So this y of 2k multiplied by a plus x of 2k. So this is x of 2k. So this is the incremental block filter structure with L equal to 2. So now in this case, total number of multipliers used 1, 2 and 3, and 3 is basically 2L minus 1. 2 into 2 4 minus 1, that is 3. Okay, so by using the incremental computation technique, one multiplication operation is reduced. Okay, but as a result latency is increased by 1. How? So during the first cycle y of 2k will be computed. Y of 2k plus 1 cannot be computed directly because it has to wait for the generation of y of 2k. After that, with the help of y of 2k, y of 2k plus 1 can be calculated. So there is a gap of one cycle. Okay, in the first cycle we will receive y of 2k, and then in the next cycle we will receive y of 2k plus 1, and after the third cycle onwards we will receive two samples simultaneously. Okay, so initially we have to wait for the one clock cycle to receive both the inputs. After that, in each clock cycle we will receive two output samples. Okay, so this is how the sampling rate will be doubled. Okay, so this is how you can design a parallel structure for a given IIR filter, and you can reduce the hardware complexity by the incremental computation technique, and this method is applicable to all the first order IIR filter.